Okay, this video is for Gauss' Law problem 4a. In Gauss' Law problem 4a, we had a charged sphere with a radius big R, and we talked about an enclosed sphere with a radius little r that was inside of our charged object. So for this example, the radius little r of our Gaussian surface is less than the radius big R of our charged object. So to start solving for the electric field enclosed by our Gaussian surface, we have to recognize a few parts. On the left hand side, we are dealing with the electric field for the surface area. This double integral here, ds, will integrate out to become the surface area of the Gaussian surface we're dealing with, and here it is a sphere. So the surface area of a sphere is 4 pi r squared. In this case it's little r squared, because little r is the radius of our Gaussian surface that we're finding the surface area for. So this takes care of the left hand side. That'll talk about the surface area of our enclosed object that contains all of the charge we're trying to measure. On the left hand side, on the right hand side, we have this QE refers to the charge enclosed by the Gaussian surface. So to measure the charge enclosed, we have a certain charge density of our charged object, which is measured in rho, which is our coulombs per meters cubed, times the volume that the Gaussian surface actually encloses with the volume of the charge the Gaussian surface actually encloses. So this is going to be 4/3 pi little r cubed, because we're talking about the volume of the Gaussian surface that encloses the charge we're trying to measure. And this piece here will be equal to coulombs per meters cubed. This come out to be meters cubed, so this will be equal to coulombs, which is the unit for our charge Q, and then we're talking about the charge Q inside the Gaussian surface, so it's the charge enclosed. So this, in fact, this numerator here is equal to the charge enclosed by the Gaussian surface over epsilon naught. So we need to find some way to talk about rho here. Now we say rho is equal to the charge of our object over the volume of the object. It's the distribution of charge over the entire object. So we have to talk about the charge it has over the amount of volume it takes up. So we can say that our charge density rho is equal to Q, the charge of our charged object, our sphere here, over the volume of the charged sphere itself, which in this case will be 4/3 pi big R cubed, because big R is the radius of our sphere and this whole denominator here is the volume of a sphere. So this gives us the charge that the sphere has distributed over some volume that the sphere takes up. That's equal to our charge density rho. So we can use this charge density and plug it into Gauss's law to solve for some electric field dependent on the charge of our object. So we'll get Q over 4/3 pi big R cubed times the 4/3 pi little r cubed, or the volume from our enclosed surface. Now here you'll see that the fraction 4/3 and the value pi cancel from our equation, and we're left with the electric field times the surface area of our Gaussian surface is equal to the charge of our object over epsilon naught times a ratio of the volumes of our charged object and our Gaussian surface. So now that we found some respective quantity that's equal to the electric field and the surface area of our Gaussian surface, we can go ahead and solve for the electric field within our enclosed surface that this whole right hand side gives us. So we have 1 over the 4 pi epsilon naught q over our volume for q over our big R cubed, the volume of our charged object, and here we have a little r squared and a little r cubed, so we'll just be left with little r to the first power on our right hand side. This here simplifies out. This value here is equal to our quantity K times our charge of our object Q times the radius of our Gaussian surface over the respective volume of our charged object. And the units for this come out to be newtons per coulomb, which is in fact the units for our electric field. And having followed Gauss's law, using proper substitution, this should be the electric field for the area enclosed by the Gaussian surface described in this problem.